Thus far, we focused on the operation on spin qubits. Now we will discuss the performance of qubits. In particular, how long can a qubit remain in its state? We can distinguish between two sorts of errors. In information language, we would denote them as bit and phase flip errors. A bit flip error is an amplitude error and corresponds to a process where a qubit, for example initially in the state spin up, relaxes to the spin down state. A phase flip error is an error where the phase of the quantum state is changed. Note that the amplitude in the spin up spin down basis is not affected. From an information perspective, it may seem that these two errors are similar kinds of errors. Indeed, if we were to apply a basis transformation using the Pauli matrices, a phase flip error can be transformed into a bit flip error. However, if we inspect the physical system, we see that phase and bit flip errors can be sensitive to different noise sources. As we learned in the beginning, an electron spin evolves in time with the Larmor frequency. If the Larmor frequency changes over time, this will lead to an accumulative phase, and thus a phase error. Examples that lead to these fluctuations are fluctuations in the external magnetic field, fluctuations in a microwave source used to operate the qubits, but also in the g-factor of the qubit. These same errors will not directly lead to bit flip errors. Their energy is not sufficient and will not cause a relaxation of an electron spin to its ground state. Spin relaxation typically requires the emission of a phonon through the interaction between the electron and the lattice. The effectiveness of this process depends on various mechanisms, like the strength of the spin-orbit coupling and many materials properties. But nonetheless, for electron spin qubits, spin relaxation is commonly much less likely to occur than spin dephasing, and we therefore mostly care about the phase coherence. We will now examine how these errors are characterized. The probability for a bit flip error to occur can be assessed by measuring the spin relaxation time. We initialize a spin qubit in its ground state, for example by using the Elzerman method as described before. Then we apply a pi pulse by applying a microwave signal on resonance with the spin qubit, such that the electron spin is in the spin-up state. After that, we monitor the time it takes before the spin qubit relaxes to the ground state. The characteristic timescale over which the spin relaxes to its ground state is called the T1 time. From experiments, we have learned that the T1 time can be seconds long. Indeed, an eternity in a quantum world. Measuring the phase requires a slightly different approach. Again, we initialize in the spin down state, but then we apply a pion 2 pulse, such that the electron spin is pointing on the equator of the Bloch sphere. We end the sequence by applying another pion 2 pulse. This should result in an end state where the electron spin is in the spin-up state. However, if we vary the time in between those two pion 2 pulses, we will observe that after a certain time, the spin qubit will no longer rotate to the spin-up state. Instead, it will remain on the equator. Indeed, this is the time where the qubit is completely dephased. The characteristic timescale over which the qubit loses its phase is called the T2 star time, and the experiment we just described is called the Ramsey experiment. Is the T2 star time the end of the story? No. We may be able to extend the coherence time by just applying more pulses. Examples of such sequences are the CP and the CPMG sequences. In these sequences, we apply in between the two pion 2 pulses additional pi pulses at specific times. The situation where a single pi pulse is applied is called a Hahn echo. If we apply a single pi pulse in the middle of the sequence, we can cancel some of the noise. Consider a spin pointing on the equator. If the Larmor frequency is different from the microwave source clock, a phase will accumulate over time. Thus, the spin will evolve over the equator. Now, if we apply a pi pulse after time tau2 and wait that same time tau2 again, the spin will evolve the exact same amount if the noise has not changed. Due to the pi rotation, the spin will always end in the same final state, thus correcting any noise that is constant over the time over the experiment. Indeed, if the noise fluctuates within the time of the experiment, it is no longer guaranteed that the phase evolution before and after the pi pulse is identical, and thus we do not correct for high-frequency noise. However, low-frequency noise is a major noise source for electron spin qubits. A T2 star has been measured as long as 120 microseconds using isotopically purified silicon-28. This time could be extended to beyond a millisecond by executing a Hahn echo sequence. Instead of including a single pi pulse, a sequence containing many pi pulses can correct for noise with higher frequencies. An example of such a sequence is a CPMG sequence. Using this method, quantum coherence could be maintained for 28 milliseconds.